very happy to welcome Peter Varju from Cambridge, and the title is Exponential Mixing of Commuting Nil-Manifold Automorphisms.
Thank you. So let me share my screen. Great. Do you see my slides?
Yes, we do.
Okay, fantastic. So thank you very much for the invitation. I'm very happy to give this talk. So first of all, I will tell you about the setup. So we will have G, which will be a simply connected nilpotent Lie group. From now on, I will always assume that my nilpotent Lie groups are connected and simply connected, and I will not repeat this. Then I will also have a discrete co-compact subgroup lambda inside this. And then the space where I'm working on is a compact nilmanifold, which is just a quotient of G mod lambda. And then there is also a Haar measure on this space. And the particular transformations that I'm interested in are the automorphisms of this space, which are just the automorphisms of the nilpotent group, which preserves the discrete co-compact subgroup. So if you don't like nilmanifolds, this is also kind of an excursion for me. So it's always good to have in mind a simple example, which is perhaps more familiar. So you can take just R to the D as the nilpotent Lie group. And for the discrete co-compact subgroup, you can take Z to the D. So that's just the standard lattice. And then X will be the torus, the D-dimensional torus. And so the automorphisms of R to the D are just invertible linear transformations. And those of them which preserve the integer lattice are just those which have matrices with integer coordinates. So so it is GLD Z. So you can have this example in mind throughout the talk, and actually everything that I'm going to say is interesting even in this setting. Okay, so let me first mention a result of Gorodnik and Spatzier, where they showed that if you look at an action of ZL, an action alpha of ZL, where the action is through automorphisms of X. So each alpha of Z is an automorphism. And so we need to assume that, that these are always ergodic, except when Z is equal to 0. Then this action is a mixing of all orders. So what does that mean? It means that if you take test functions, L infinity test functions, F1 up to Fs, and you take some elements of the acting group, and then you precompose your test functions with the action for each of these elements in the acting group, and you look at the correlation of these test functions, then it will be very close to the product of the integral of the test functions. If the minimal distance between the elements in the acting group goes to infinity. So basically what this says is that if you take this multiple correlation of your test functions twisted by the action, then it will become asymptotically uncorrelated if the distances between the acting elements are far enough. Okay, so here I would like to mention that the torus case, which I alluded to above, was done much earlier by Klaus Schmidt and Tom Ward. Are there any questions at this point?
I have a question. So on this theorem, is a specific bound on the rate of convergence depending?
Yes.
I mean,
yeah, that's exactly what I'm going to talk about in the talk. So,
okay.
Yes, they proved the rate. They proved an exponential rate, but only up to mixing of orders at most 3. So here is that statement. So again, we have an action which is where alpha of z is ergodic for all non-zero z. And then we take some theta, which will be the Hölder parameter. And then the theorem says that there are some constants eta and c such that for all test functions f1, f2, f3, which are in this theta Hölder class, if you take z1, z2, and z3 in the group acting, then if you compare this threefold correlation of the test functions with twisted by the action and with what it should be in the limit, so just the product of the integrals, then this is smaller than an exponential rate in the minimal distance between the zi, zij's times the product of the Hölder norms, the theta Hölder norms of the test functions. So this is precisely a rate in this convergence, so one comment is that of course you can't have a rate if you don't restrict your class of test functions somehow, and it's convenient to take the Hölder class, but it's not really important what it is. And then if you take mixing of order at most 3, then you can get this exponential rate. So this is what they proved, and they couldn't give a rate if you take a higher order. If you look at higher order mixing.
Can you remind what is the Hölder norm appearing there?
So it's so you take the distance. So you take 2 points at distance. Okay, how to say it? So you take f of x minus f of y, and you divide it by the theta power of x and y. And you take the supremum of this over x and y, and plus you throw in the supremum norm, just to make it a norm. So you can just consider the theta equals 1 case, and then it will be the Lipschitz norm. And so basically you lose nothing if you just think about the Lipschitz case. So that's the theta equals 1. Yeah, so also there were some earlier results in this direction by Lind, Dolgopiat. So those concern the case when you have just a single automorphism acting, so not a ZL action, but just a single one. And they proved the exponential rate. So I believe that Lind was for the ordinary mixing of order 2, and maybe Dolgopiad extended to mixing of all orders. And there were some partial results by Miles and Ward later. Okay, so the result I'm going to talk about is with Timothée Bénard, who is a postdoc here in Cambridge. And so basically what we proved is that the same result, so the same exponential rate, is true for mixings of all orders. And the only thing that changes is that the constant C becomes ineffective. So let me comment on what this means. So having effective constants means that if you tell me what the action alpha is, plus you tell me what is theta, then if I work really hard and go through every steps in my proof very carefully, then I will be able to tell you exactly what eta and C is. It is likely to be something, well, eta will be probably something reasonable and C will be probably something quite horrendous, but I could actually write down a number, something like 10 to the 10 to the 10, whatever it is. Now, if you take our result with Timothée, the situation is a bit different. So I'm happy to talk about eta. So if you ask me what eta is, I could work that out from my proof. But if you ask me what the constant C is, I have absolutely no idea. So the proof yields that there is some finite value, but it will not tell you how big it is. And so this is not just laziness on my part, but actually there is a logical reason for this. The proof will never give you anything. So you will never be able to say that it is smaller than 10 to the 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 10. Okay, and so basically the reason for this is because both of these results use some number theory inside it, and Gorodnik and Spatzier works with an effective tool, which is called Baker's theory of linear forms in logarithms, and we need to work with the Schmidt's subspace theorem with Timothée, and that's the result of the ineffectivity. Okay, so why do we care about this? So there is a conjecture by Katok and Spatzier which says the following: that if you take, so this L should be the same as this R. So if you take some L which is at least 2, and you take a genuine ZL action on a compact manifold, which is Anosov, then this will be C infinity conjugate to an action on infranil manifolds by affine automorphisms. So I'm not going to explain all the terms in this conjecture. So actually, I think that this is somewhat the meaning of some of the words are kind of deliberately vague. So part of the problem is to kind of work out what you need to assume for this to be true. Genuine. Okay, so first of all, this is not true if you take rank 1 action. So if you just take an Anosov diffeomorphism on a compact manifold, then it need not be C infinity conjugate to an affine automorphism. So you need higher rank, and then you need to make sure that this is genuinely higher rank. So it's not you didn't find some sort of rank one action in a secret way, and so this is why you need to say genuine. Okay, so infranil manifold is just something just a little bit more general than nil manifold. So basically, it's a manifold which has a finite cover by a nil manifold. So that's not much a difference. And so what is an affine automorphism? So it means that you are allowed to apply an automorphism, and after that you are allowed to apply a translation with your nilpotently group. So in the torus case, it means that you can apply these elements of GLDZ, and you can also apply a translation with in some direction. Okay, so so the reason why I mentioned this conjecture is because this shows that this kind of dynamical systems that I'm talking about are well, it's a special class of dynamical systems. But if you want to look at Anosov actions on compact manifolds, then you don't have anything else. So it's an interesting class of dynamical systems. And so in addition to that, there has been some recent partial progress towards this conjecture, first by Fischer, Kalinin, and Spatzier, and then later by Rodriguez, Hertz, and Wang. So this partial progress relies on these quantitative mixing results of Gorodnik and Spatzier that I mentioned above. However, this application only requires standard mixing, so mixing of order 2. So at this point, I don't really have an interesting application for the higher order mixing. But at least this shows that ZL actions are interesting in this problem. Okay, so here I state what Rodriguez, Hertz, and Wang proved towards this conjecture. So they say that, okay, so let alpha be an action by diffeomorphisms on a compact infranil manifold X, and let rho be its linearization. So this is an action by affine automorphisms that is topologically conjugate to alpha. So it turns out that that if you don't want C infinity conjugation only by conjugation by a continuous map, then this thing is then this always exists, and in fact this is true even in the rank 1 case, and it has been known for a long time. And the problem is really about showing that you can make this smooth. So rho is the linearization, and what you need to assume that alpha is Anosov for some z, and that the linearization rho does not have rank 1 factors. So then, if you have this, then alpha is conjugate to rho by a C infinity diffeomorphism. So basically, this establishes the conjecture in the special case when you know a priori that the manifold where you are acting in is an infranil manifold.
I have a question. If you
yes?
say Anosov action, do you mean at least one map is Anosov, or all maps in the action are Anosov?
Yes, so actually that's the difference between the result of Rodriguez, Hertz, and Wang and the earlier result of Fischer, Kalinin, and Spatzier. So as you see in the result of Rodriguez, Hertz, and Wang, they only assume that there is one element in the group for which the action is unsolved.
But before you assume it all are unsolved.
So I know actually what they need is they need more unsolved elements. Not all of them has to be unsolved. If I remember correctly, their assumption is that there must be an unsolved element in each while chamber, whatever that means. So they need several of these, and so actually in their paper, in the paper of Fischer, Gorodnik and Spatzier, they proved this result with under the assumption of having more unsolved elements, and they were actually speculating that maybe the conjecture would be false if you just have a single one. And so this is something that Rodriguez, Hertz, and Wang settled, that that it's enough in that special case, at least it's enough to assume that one element is unsolved. So I think the conjecture is somewhat open to interpretation. Any other questions? Okay, so
what does, excuse me, what does the word irreducible refer to? To the unsolved?
That's I'm not totally sure. I think that it's probably that you don't have a sub-nilmanifold where you could restrict your action.
But wait, we talked about the word genuine. So how do they?
So in the result of Rodriguez, Hertz, Wang, genuine means that if you look at the linearization, then it doesn't have a rank 1 factor. So it means that you can't, you don't have a quotient of your nilmanifold, which would be another manifold where you have an induced action by rho, and that factor through action of Z.
So it's about either about factors, either about sub-actions. About induced actions.
So what I'm saying is that so one way this one way to make a non-genuine ZL action would be to have an action of Z and then map ZL to Z and act this way. So
right.
that would be clearly cheating. But if you have something like that, then what you could do is that you could somehow construct a nilmanifold, a larger nilmanifold whose quotient is this this previous one, and you could somehow lift this non-genuine action to something which doesn't factor through a rank 1 action.
I'm not sure, but how this refers to the irreducibility.
Irreducible and genuine are not related, I believe.
Okay.
They are separate conditions. So actually, it's not clear that it's needed. So in this special case dealt with by Rodriguez, Hertz, and Wang, you can drop that condition. Okay, so then I would like to talk a bit about the proof of our theorem with Timothée. Okay, so let's fix some elements Z1 up to Zs in the acting group. And then let H be the image of the group G in G to the S under this map. So each coordinate is mapped to G twisted by the action. So alpha Z1 up to alpha ZS. So this is a twisted embedding of G inside G to the S. Okay, so what we care about is this integral. So this is the correlation of F1 up to Fs twisted with alpha Z1 up to alpha Zs. And so you can observe that this is actually equal to an integral on GS of the function capital F, which is just the product of the test functions F1 up to Fs evaluated at the coordinates. But we are not integrating against the Haar measure on GS, but we are integrating against the Haar measure on H. So this is there is really no content in this observation. It is really a tautology. So basically, what we need to understand is that this twisted copy of G inside GS. So how uniformly is it distributed inside G to the S when you are take the quotient by the when you look at the image on the Nil manifold. So your Nil manifold G mod lambda is embedded in this twisted way inside G to the S mod lambda to the S, and the question is that how equidistributed is this embedding. So also note that the Hölder norm of capital F can be bounded by the product of the Hölder norms of the original test functions. So if we can really estimate this integral in terms of the Hölder norm of capital F, then we will be in good business. So now I'm going to state a result which is a bit long to state, but so let's begin. So we need to fix our theta parameter, which will be the Hölder exponent. So if you want, you can just take theta equals 1 and think about Lipschitz functions. So then I need my nilpotent Lie group and my discrete co-compact subgroup, and I will denote by G is Lie algebra, and I endow it with a rational structure such that the inverse image of the exponent under the exponential map of my discrete co-compact group will be rational points. So if this is confusing, then you can just consider the torus case. So in the torus case, G will be R to the D, lambda will be Z to the D. The Lie algebra itself will also be R to the D, and so the Q structure will be just the usual one. So basically, the exponential map is the identity. So it will have the ordinary Q structure. And then, so I look at the abelianization of this Lie algebra, and that will be some vector space over R, so I can identify it with R to the D. And I want to do this in such a way that it respects the Q structure. So if you are thinking about the torus case, then you can basically ignore this because you already, so then the commutator will be trivial. So the R to the D will be already the Abelianization of the algebra. And you have your ordinary Q structure. And so I write pi for the projection map from the Lie algebra to the Abelianization. Okay, again in the torus case, you can ignore this one because it will be the identity. Okay, so the proposition continues. So with this setup, there are some constants C and kappa such that the following holds. So I need some closed connected subgroup H inside G such that it intersects my lattice lambda in a co-compact subgroup. So this means that when I look at the image of H inside the Nil manifold, it will be a subnil manifold. And then I denote by capital A the length of the shortest non-zero integer vector in the orthogonal complement of pi of H. So what is H? H is the Lie algebra of capital H. And pi of H is its projection to the Abelianization. And you look at its orthogonal complement, and you look for integer vectors there. And you look at what is the shortest one, and that will be the length of it will be A. Okay, so then the conclusion is that if you take a test function on G mod lambda, then if you look at its integral with respect to the Haar measure on H, so you integrate it on the subnil manifold. So this is supposed to be mu H, and you compare it with the integral on the full Nil manifold. Then you can estimate this difference by A to the minus kappa times the Hölder norm of the test function. So basically what this says is that if you don't have a short integer vector in the orthogonal complement of pi of H, then your subnil manifold given by H will be very uniformly distributed in the Nil manifold G mod lambda. Okay, so I will talk a little bit more about this and just talk through this again in the torus case. But before I do that, I just want to point out how this is going to be used. So when you apply this, then you apply it with G to be the S power of the original G. And this H inside it will be this twisted embedding of the original G. And then this this estimate that you get here is precisely what you want to get at the end. So the integral of this capital F, where this capital F is just the product of the test functions evaluated at the individual coordinates. So this one will be this correlation, this S-fold correlation, and the other guy will be just the product of the integrals. So if
Isn't an H missing?
Yeah, an H is missing here, so it should be mu H. Sorry. So this is this proposition will reduce our problem to estimating this shortest non-zero integer vector. Okay, so again, what does this say in the torus case? Well, so now you have a torus, and you inside this torus you have a subtorus. What does it mean? You take a subspace of R to the D, which needs to be a rational subspace spanned by rational vectors, and then if you so this subspace will sit inside the torus in such a way that that it will wrap around and give you another torus, and it will give you a subtorus. And so what this proposition says is that if you want to find out how close this subtorus is to equidistribution in the big torus, then what you need to do is that you look at the this subspace, and you look at which gives you the subtorus. You look at its orthogonal complement, and what you hope is that you will not find a short integer vector in the orthogonal complement. And if you don't find a short integer vector in the orthogonal complement, then this will sit inside your torus in a very equidistributed manner. So I hope that at least this is something that's believable. And actually, you can prove this using Fourier analysis in a very direct way. What's more complicated is to do the general nilmanifold case, and that relies on some results of Green and Tau on polynomial progressions in nilmanifold. So they have a general result about what they call polynomial progressions, and when do they equidistribute, and you can approximate your subnil manifold with a very dense polynomial progression, and you can just apply the result, and this will come out of it very quickly. Okay, so let me ask if you want to ask a question at this point. So if not, then I will continue. So okay, so first of all, this proposition also reduces the problem to the torus case. So as you can see, this estimate, this error term that you have here, it depends only on the abelianization of H, how the abelianization of H sits inside the abelianization of G. So basically from now on, it will be enough to consider the torus case. So now let's consider ZL action. So an homomorphism from ZL to GLDZ, and such that no eigenvalue of alpha of z is a root of unity for any non-zero z. This is equivalent to the ergodicity assumption that we made. Then, if we look at some z1 up to zs in the acting group such that they are far from each other, further from each other than capital N. So then we want to show that there are no integer vectors such that their length is bounded by exponential in n with a small constant c, and such a way that this is orthogonal to this twisted embedding of R to the D. So what does that mean? It means that that you have this equation. So what I formalized here is that that there is no short integer vector in the orthogonal complement of this twisted embedding of R to the D inside R to the D to the S.
But wait, I don't follow. Why would this be important? If it's short or not short?
So because this capital A, this is the length of the shortest non-zero integer vector in the orthogonal complement. So this is what comes in this estimate. So you want this capital A to be large. You want it to be exponentially large in capital N.
So you are not proving now the proposition.
No, I'm not proving the proposition. Sorry. What I wanted to say is that I hope that it's plausible. And so in the torus case, you can work it out very easily using Fourier analysis. In the general case of Nil manifolds, it's much more difficult. So that it's one of the unasked papers of Green and Tao, and it's like 80 pages where they prove these results about these polynomial progressions inside in Nil manifolds and directed distribution. It's quite involved. So what I'm talking about now is that if you believe this proposition, then how you can go on with the proof.
But why isn't it enough that there is an A? Just use that there is some constant. Why wouldn't this be enough?
So so we want this quantitative mixing. So what I want is that as my capital N increases, I want this A to increase too.
Okay.
And so I claim this exponential rate. So I need to show that that there are no integer vectors which are shorter than exponential in capital N, such that you have this equation. Okay, so this will come down to some number theory. This is kind of a Diophantine equation, if you like, and I want to talk a little bit about what kind of number theory comes in. So we assume that alpha, the action alpha is diagonalizable. So that means that there are some characters z to the L to non-zero complex numbers and some vectors in C to the D, such that so these will be the eigenvectors. If you act on the eigenvector by alpha to the z, then it acts by multiplying with this character chi j. So this is a special case because it doesn't have to be diagonalizable, but the general case is not more difficult at all, and this just makes the discussion easier. So what we are going to do is we plug in Wj to my starred equation that I have here, and then the action alpha of zx we'll just pull out. So you pull out the chi j of z, and then you have an equation of this kind. So a linear combination of the chi j z's with these a1 wj as wj will vanish. Okay, so we get an equation of this kind, and so basically the next thing that I want to talk about is that these numbers chi j z are very special, and because they are very special, you don't expect that they would satisfy an equation of like this. So for this I need to talk a little bit about number theory. So I will have a number field, capital K, which is the number field generated by chi of jz for all z in ZL. Okay, so what is this chi j z? These will be the eigenvalues of some matrix in GL dz. So if you want to find the eigenvalues, then you need to solve the characteristic polynomial of that matrix. The characteristic polynomial of that matrix will be some polynomial with integer coefficients. So these eigenvalues will be algebraic numbers. And moreover, you can work out the leading coefficient and the constant coefficient of these polynomials. And you will find that they will be plus or minus 1. So in fact, these numbers that you get will be algebraic integers. So an algebraic number is an algebraic integer when you look at if it's a root of a polynomial with integer coefficients whose leading coefficient is 1. Okay, so I denote by OK the ring of integers inside K. So that's a subring of K which consists of all the algebraic integers inside K. And I denote by OK times the units inside OK. So that will be the algebraic integers which are invertible. So their so their reciprocal is also an algebraic integer. So the observation is that that chi j of zi is a unit for any choice of j and I. And why is that? Is that because when you work out the characteristic polynomial, so the equation that you need to solve to find the eigenvalues, then not only the leading coefficient but also the constant coefficient will be plus or minus 1. and for this reason you can, or maybe another way to see this is that so if you take minus zi, then you get the reciprocal of the eigenvalue. And so if you believe me that this is an algebraic integer, then its reciprocal will also be an algebraic integer, and precisely that's what it means to be a unit. Now, units are very special elements inside a number field. So there is a result called the Dirichlet's unit theorem, which says that this is a finite rank abelian group inside the multiplicative group of K. So you have some y1 up to yr for some r, which are some fixed elements inside your number field, and you can get all units by taking integer powers of these and multiplying together. So one thing is missing from my slide is that these b1 up to br are supposed to be integers. So so the only thing that I'm trying to say here is that there are very few of these numbers inside your number field. If you look at and for this reason, you don't expect that that an equation like this will hold. Okay, so I'm going to state another result which will complete the proof of the theorem, and then I will finish the talk. And for this, I need to introduce some further notation. So I write capital S for the embeddings of my number field into the complex numbers. So there are as many of these as the degree of the number field. And so I use a somewhat strange convention that I include both copies from a pair of complex conjugate embeddings. So if you have an embedding of k into the complex number which doesn't sit inside the real numbers, then you can also apply complex conjugation and you get a different embedding. And I want to have both of them in my set S. And then for each such embedding, I can pull back the absolute value from the complex numbers to k. So I will have an absolute value on my number field, which pulls back the absolute value on the complex numbers via this embedding. So this way, I have many of these absolute values, and then I need two quantities. So for the first one is a standard one. It's called the height. So what I do is that I take each embedding and I look at so I have a vector of units, and I take the maximum of the absolute values of each coordinate, and I multiply together for each choice of the absolute value. And then it turns out that the proper way to normalize this is that you take it to the power 1 over the degree of the number field. This is not very important for what I'm going to say, but if you want to define this in a way which makes it independent from the number field k, then this is the right thing to do. Okay, and then I will also have another number kappa, which does the following. So I can take an arbitrary subset of my indices, but it has to be at least 2 index. And you calculate this height for this. So basically, I can drop some elements from my vector. And then I look at the height that I get, and I take it to some power, depending on the size of how many indices I got at the end. Okay, and then I also consider this subset OKH. This is the way you should think about this is that this is a box inside the ring of integers of K. So okay, so maybe the way to think about this is that you embed K in the complex numbers in all possible ways, and then so it turns out that if you look at the image of the ring of integers in complex numbers to the power d, then you get a lattice, and this is a box with side length h in that embedding. Okay, so here is the final proposition. So let K be my number field. Then I need to fix some positive epsilon, and the number d at least 2. Then I have an ineffective constant such that the following holds. I take a vector consisting of units, and I take some elements a1 up to as in this box. So these are integers in the ring of integers of K, which are contained in this box H. So then, not all of them are 0, and H is some parameter. Now, suppose that I have this equation. So I have a linear combination of my units with the coefficients being these algebraic integers in this box. So suppose that this linear combination vanishes, then it must be the case that this h parameter is at least some constant times this kappa parameter of my units to the power 1 minus epsilon. And so if you work out what this means, then this will turn out to contradict this equation. So it will show that that you will not find a solution of this equation, at least so only there will be only finitely many situations when this happens. So, and then so if that capital N was sufficiently large that you had before, then this equation will not have a solution. So now I only want to mention that this result is based on Wolfgang Schmidt's subspace theorem, which is a powerful tool in Diophantine analysis. It is a generalization of Roth's theorem in Diophantine approximation. So the one that says that if you have an algebraic number and you want to approximate it by a rational number P over Q, then you will never do better than 1 over Q to the 2 plus epsilon. I also should mention here that that this is something which is very close to a result of Evertse from the 80s. So this is a slight modification of that. Okay, so Jonathan did not tell me how long I should speak, but I think that 1 hour is enough, so I will stop here, and thank you for your attention.
Okay, thank you very much. This is very interesting. Of course, highly non-trivial. Are there any questions? I actually have a question about ineffectiveness in Schmidt's subspace theorem. Probably this is well known. Is it already ineffective in this Ross case?
Yes, yes.
And what is the reason for that?
Yeah, so it's kind of you know that there is this saying that the lightning will never strike twice in the same tree.
Okay.
Okay, so if you accept this, then it means that there is some constant C, such that after year C, the lightning will not strike your tree. Because two things can happen: either your tree will never be struck, then you can take for C 2022 if you want. The other option is that your tree will be struck at some point in the future, and then in that case you can take for C that year. Now this will give you this ineffective C, because it is very unlikely that your tree would be struck, but you don't know this, so you can't write down a number for C. You see what I mean?
Yes.
So basically, the way Roth's theorem, the proof of Roth's theorem works, is that you assume that you have a sequence of rational approximation to your number of a particular finite sequence, which have to satisfy certain properties. And if you have that, then you can do a lot of mumbo jumbo, and at the end of that, you can get a contradiction. And I don't know, maybe this to do this, you will need 10 approximation. And if you find the 10 approximation of your algebraic number, then you can write down an effective constant. But if you can't find those 10 approximation, you only find 9 of them, then the only thing you can say is that if there are no more, then it's good. If there is one more, then it's also good. But the constant that you get, it depends on this hypothetical further approximation that you couldn't find. Do you see what I mean?
I think so.
So you can't derive a contradiction by just assuming that you have a single approximation. So I mean what comes out in this application, it's somewhat more complicated, and I don't want to claim that I fully understand it. But basically, kind of what it says is that if you just assume that this equation has a solution, then you will not be able to derive a contradiction, assuming just you have a single solution. But if you assume that you have many solutions of various kinds which are sufficiently independent and sufficiently satisfy some things that you need, then from that assumption you can derive a contradiction. And basically what this gives you at the end of the day is that you can have only finitely many counterexamples. But you don't have any idea about is that how big that counterexamples could be.
Okay. Are there any other questions? Okay, so let's thank Peter again.
Thank you.
Thank you very much. It's very interesting.
Thank you. Thank you, Peter. Thanks everybody to listen also. Next week, Gennady Levin will speak. Are you there, Gennady? Okay.
Yes, I'm here.
You are here, yes. You confirm.
I was here.
Okay, thank you.
All right, thank you. Goodbye.
Goodbye.
Thank you. Thank you. Bye bye.